All right, everybody, welcome back. Mr. Martin here. This is 9.1 greatest common factor. We are going to talk about the greatest common factor, and we're going to learn this thing called the zero product rule. This is going to help us solve for zeros of a function. All right, first things first, things to know. You guys should know a lot of these words. This is mostly recall. You're going to hear me using them throughout this unit, so it's kind of good that we do a little bit of a refresher. So remember that a product, this is made of two or more factors. Factors, things that multiply to each other, they create that product. Okay, and it could be a number, could be a variable, could be a number and a variable, or a variable. Any way you want, whatever. It's your money. Okay. Factors can either be individual numbers and or variables. So I mean, we got an example. It could just be 3. Could be maybe a variable with a coefficient like 2h. Those would work. Or they can be expressions. Remember, an expression can look something like x plus 9. We'll touch on this a little bit later. All right, remember, anytime if you need to pause the video, make sure you get this information down. All right, here is the main event, the greatest common factor, or GCF. This is the greatest number and or variable that is common throughout. That common throughout is a integral part of this lesson. And also every term of an expression. So this whole last piece right here is really important. And then remember, we got prime numbers, we got composite numbers. Remember, this is a little bit of background, but prime only can be divided by 1 in itself. Composite can be divided by some other numbers. We are going to break those down just as we always do. And then we got this thing called the zero product rule. This tells us if we had something like a times b equals 0, then if a is 0 or b is 0, it works. Or if both a and b are 0, any way you slice it, you multiply and dice it, those are going to equal 0. That's just how it is with the zero product rules. Them's the rules. All right. Example number 1, we got some prime factorization. We got some factor trees. You might have seen this in my review section at the beginning of the year. If you came to me late, you might have missed it. Maybe you forgot it. Maybe you know how to do it. I'm going to walk you through it. Let's check it out. So remember, factor tree, we want to move down and we want to get them down to our prime numbers. So a good rule of thumb is anytime you have an even number, your smallest prime number is the number 2. So let's just start dividing this by 2. Half of 84 is going to be what? 42? I think so. So we got 42. And then we got another even number. Let's half that up. 42, half of that is going to be 21. And then 21 is going to be, can we divide that by 2? We sure cannot. So then we go up to the next prime number, 3. Let's divide that by 3, and that's going to be 3 times 7. So remember, we are looking for the outer part of this factor tree. Okay, remember, and if I'm going a little fast, you don't remember this, you can go back to chapter R and watch it be a little bit more in depth. But basically, these are all factors, and remember, factors are multiplying. So we got 2 times 2 times 3 times 7. So that is the fully prime factored form of this number. Okay, I'm going to do the one right below it just because this one has variables. We do it the same way. So let's do this 104. We got an even number. We're going to half that up. That's going to be 52, right? Half of 52 is going to be 26. And then half of 26 is going to be what? 13. And if we recall right, 13 is a prime number. So I think we are done with the numbers here. And I'm just circling those up. Remember, we are using this outer row down to these bottom 2. These ones on the right do not matter to us. But we also got this variable. How can we break this down? Well, if we multiplied x times x times x times x times x, we would get x to the 5th. So that means there are 5 x's here. These are all factors. So then our fully prime factored value down at the bottom would be 2 times 2 times 2. 2 times 2 times 2 times 13. And then we got times 5x's. So let's put those in, 4 and 5. And then I'm going to put my blue box around it because I like how it looks. Very patriotic, red, white, and blue right here. So I want you to pause the video. You're going to do these two on the right and then come on back. Alright, welcome back. So this is what I got. This top one, I broke it down 3 times 3 times 7. And then down here we had 59. That stayed as is because that's a prime. Can't break it down anymore. And then we had x times x times x. And then we got times y, and times z. So hopefully you got the same thing I got. Now you might be asking yourself, why are we reviewing this? This was so long ago. Well, this could possibly help your brain when you are doing some of these factoring problems. All right, let's take a look at example number 2. So we got another piece of recall. Why so much recall? Well, that's why we learned this stuff in the first place, because we know we're going to use it later. Okay, remember distribution. Distribution is when we had something on the outside of a parentheses, and if we had more than one term, we had to multiply it to every term inside the parenthesis. So we got a 5 times a 3. That is going to give me a 15. X times x would give me x to the second power. And then 5x times positive 6 would be a positive 30x. Okay, so nothing new here. You've seen this before. You know what it looks like. This is what distribution is. When we do factoring, we are actually doing the opposite of distribution. We are working backwards. Instead of putting something in, we are taking something out. So if you look here, we do not have a set of parentheses like we did on the left. If you looked after we distributed, when we went from here to here, it went parentheses to no parentheses. So now we're going to work the other way, and we're going to go from no parentheses to something with a parentheses. And the reason I showed you those factor trees is because we're going to see a little bit of this at work. We got these two terms here. We're going to fully prime factor both of these terms. So what I'm going to do is I'm going to write this first one up here, and I'm going to write this second one over here. So let's prime factor this 28. That is going to be 2 and 14. Oops. 2 and 14. And then this 14 is going to be 2 and 7. Okay. And then we got the x times x. Okay, so this is everything that's done right here. And then this 56 is going to be 2 and, what is that, 28? And then 28 will be 2 and 14. And then 14 will be 2 and 7. And then we have just a single x right here. So remember, if we go back to our definition, let's do that real quick here. The greatest common factor is looking for the greatest amount of numbers and or variables common throughout every term. Okay, so as we're working throughout this, we have two terms. We want the greatest amount that is common, so we're basically trying to match stuff up. Well, here on this first one, I got 2 2's, right? And on the left, I also have 2 2's. Okay, what else is common throughout both of these terms? Well, we have a 7 that's common, so 7 can match that 7. What about our variables? Well, I got an x here, and I got an x here. Okay, so I got an extra x. Do I have an extra x over here? I do not. I have this 2. Do I have another 2 that I can match it up to? I do not. So we've taken the greatest amount that we can from both of these. And remember, these are all factors, so they are all multiplying. So let's actually see what these multiply to. So 2 times 2 times 7 times x would give me 28x. And then we want to see, is it the same on the other side? 2 times 2 times 7 times x. Well, if it's the exact same thing, then it should be the same. So this right here is our GCF. We found the greatest common factor between every term in this expression. Okay, but we do have some leftovers. So from this first term, we used these values, we used this x. What do we have left over? We got this x. On the right side, what do we have left over? Well, we got this 2. So I'm going to put that here, and I'm going to put that here. Okay? So remember, working the other way, there's something on the outside of a parenthesis. We want the same thing too. Okay, so what can we take out? This greatest common factor of 28x. And we know we're going to have that parenthesis. What did we leave behind? Well, we left a x and a positive 2. Now, let's see if we did it correctly. If we multiplied this back, let me use a different color besides blue. I'll go purple. If we move this back by distributing, remember, if we are factoring, which is the opposite, we should get back to where we started. 28x times x, that's going to give me 28x squared. 28x times 2, that gives me 56x. And it looks like we are back where we started. Okay, so one way you can do this, if you have a hard time figuring out what is the greatest common factor between these just by eyeballing it, you can always break it down into your factor trees and find the matching pairs. This is where having an idea of your common multiples will come in handy. All right, let's take a look at example number 3. All right, so we got these 3 different columns. One says factoring out just a number. Sometimes you can only factor out a number. Sometimes you can only factor out a variable. Sometimes you can factor out both. And then sometimes you can't even factor out anything. But once you see each of these, you'll know when you can't factor out nothing, when you can factor out nothing, or can't factor out nothing, can't factor out anything. All right, I'm getting off track here. All right, so if we know we only have a number that we can factor out, we can easily eyeball that because do both terms have a variable? This one only has a variable right there. So if they both don't have a variable, we cannot factor anything out. All right, so we want to look at 12 and 16. What is the greatest number that we can divide into both of these evenly? Well, we know we can do a 2, but can we go bigger than a 2? What about a 4? I believe so. So 12 divided by 4 is going to give me 3, and we didn't take the x out. Negative 16 divided by 4 is going to be negative 4. And then if you want to, you can fact check and multiply that back out. All right, we have factoring out a variable. Well, if we looked at both of our coefficients, do these have a greatest common factor? Is there a number that can divide into 7 and 15? Nope. 7 is prime, so, you know, nothing that can go into 7 can go into 15. It just does not work. But if we look at our variables, looks like we have the same variable in both terms. Let's go ahead and take one out. Here we have 2 a's, here we have 1 a. So the most I can take out is always my smallest amount. So 7a squared divided by a is going to be 7a. Remember, if you had 2 a's, you took one out, you only have one left. 15a divided by a, we had 1a, we took it away, and we just have no more a. And we are good. Here we can factor out something in both. Well, we got 14 and 35. All of my football heads know that 7 can go into both of these numbers because these are football scores, considering you are making your field goals. So it looks like we can take out a 7. We got 3 b's and 2 b's. We always take out the smallest amount. 14 divided by 7 is going to give me a 2. We had 3, we took 2, we're left with 1. 35 divided by 7 is a positive 5. We had 2 b's, we took 2 b's away, so that means we have no more b's. Alright, and that is done. I bet you know what's coming with this bottom row. I am going to pause the video right here. You are going to do the rest yourself. Then come on back. All right, welcome back. Hopefully you got what I got here. So this first one, I took out a 3. That is the largest number that can divide into all of these terms. The second one, remember, if it is only the variable coming out, or anytime you take a variable out, you always take out the smallest exponent. So 5, 4, and 2, I took out the 2. Now this is something that I've seen people mess up on, okay? The largest number that can go into 4 and 16 is 4. The smallest number is x squared. Remember, after you take out this GCF, you are taking this number divided by this number. 16 divided by 4 is 4. X to the 4th divided by x to the 2. If you remember your exponent rules, you are subtracting. Okay? But for this second term, I see this many times where people just either put a 0 there or leave it blank. But you got to ask yourself, you are taking 4x squared divided by 4x squared. Now what does that look like if you write it like this? Anything over itself is always equal to 1. So do not forget to put that 1 right there. That is highly critical. Anytime you have something divided by exactly itself, you got to leave a 1 in that place, because that's what it means. 4 over 4, 1. X squared over x squared, 1. Okay, that is just how it goes. All right, and for example number 4, this is our last example. Okay, we have what we call the zero product rule. Okay, before I jump into this, I want you to write this little piece of extra notes down at the bottom. And this says, anytime we are solving, set every factor equal to 0 and solve. But you must always have all factors on one side set equal to 0. It is important that you do that. Okay, that is your first step into solving. All right, so do we meet that special note? Do we have all of our factors on one side and it is set equal to 0? Well, it looks like it is to me. So this 15 on the outside, we do not have a variable there, so we cannot set 15 equal to 0 because that just doesn't make sense. 15 equals 0? No, that's a lie. That does not equal 0. So we can't do anything with that 15. But we do have this 2x minus 3. So we are going to set that equal to 0. And then we're going to solve. What does x equal? Well, how do we do that? Well, we've got to add 3 to both sides. Then we get 2x equals 3. And then we got to divide both sides by 2. And x is equal to 3 halves. So this tells us if we put in 3 halves for x, that's going to make this piece a 0. And then 0 times 15 would give me 0. So this is my solution. So you could write it as x equals, or you could do your little set notation, fancy squiggly brackets, and put it like that. All right, second example. Are we set equal to 0? No, we got 8a squared equals 16a. We want everything to one side. How do we do that? Well, we simply subtract one of these from both sides. All right, so now we got 8a squared minus 16a is equal to, what's 16a minus 16a? 0. All right, boom, it did the work for us. All right, we want to ask ourselves first, can we factor anything out? Is there anything common between both these terms? Well, numbers and variables alike, yes, there are. So what number can go into 8 and 16? That is 8. We got 2a's and we got 1a. We always take out the smallest. Now 8a squared divided by 8a is just going to be a. 16, negative 16 rather, divided by 8 is negative 2. We had an a, we took it away, there are no more a's. And then this is equal to 0. Looks like we got 2 factors here that have variables, so we need to set both of these equal to 0. So we got 8a equals 0. How do I solve? Well, I divide both sides by 8, and a equals 0. All right, then I got a minus 2 is equal to 0. How do I solve this? Add 2 to both sides, and we get a equals 2. So here there are 2 different values that would make this 0. Okay, so we would put that into our solution set. 0, 2. All right, well, I'm going to let you do the last one, but before we jump into it, how many factors do you think we need to set equal to 0 here? I'm going to count down. 3. That's it. 3. You thought I was going to count down to 0. No, there are 3. 1, 2, and 3. All right, go ahead. You set them to 0, and then come on back. All right, welcome back. So I got -4/7, 0, and 2. Hopefully that's what you got as well. Remember, do not let fractions fool you. These might be some of those answers. All right, that is all I have for you guys today. Make sure you do that practice. Make sure you ask for help. Reach out anytime that you need it. I had a blast. I will catch you on the next one. Peace.